look at me like I'm crazy. When I shut my feelings out, you look at me like I'm different. Still you stay cause you feel something real. Get so lost in my moments. Doesn't mean I don't need you. I fell in love with your colors. They kinda tell me what I'm thinking. Fell in love with the way we are and the way we lose it. There's something different about us.
Good morning.
And the reason why we say
Morning.
Hi, Chris.
How are you?
Good. How are you doing on this fine day?
Nice. It's raining. That's
Yeah.
good.
A little bit. Are we
Little
expecting?
bit.
I think we're expecting more later. Are we expecting like more than the sprinkle we got?
Well, I'm up in the foothills, so I think we're supposed to get a couple of inches.
Oh, nice. We're like at 1/4 of an inch. A little tiny bit. But if we get up in the hills, that's better than getting it down here in the valley.
Yeah.
Because then it flows down. Well, can you believe it? We are at the end of, I think, week 12. So we just have 13, 14, 15, and 16. Got 4 more weeks to go. So we're kind of at the apex of this course, right? This is the group of assignments that really puts together a lot of the concepts that we've been learning over the past 12 weeks. And so this is probably the most challenging assignment. Beyond this, we have networking, which compared to this is going to be a walk in the park. So we got a lot of concepts that we've learned, and then I was going through the course website last night and went, oops, I forgot to talk about the level 10 assignment, which was called loading the dictionary. I was so excited about doing the sorting and searching that I completely bypassed that. So we kind of have to go back and cover some of the material that was in that assignment. Let's take a look at it. So let me bring this down here. So here's the assignment. You're going to be writing a program to load a dictionary passwords into an array, then search the array for entries. We've actually already kind of done this, right? We've written a program that loads in a file with a bunch of words in it, and then constructs another array, and that second array points to the entries in the first array. You'll be using some of the concepts we've learned about recently, like dynamically allocated memory, which we've done, but this thing about resizing arrays we have not talked about. And that was one of the shortcomings of our program. And I briefly mentioned at the time, I wanted to show you a different way of loading this dictionary, and then I completely zoop, that went out of my brain and we didn't actually talk about it. Then we have searching through the array, which we've already done, and we've done memory management and debugging. So the only thing we really haven't done is this resizing the array thing here. If you recall from that program that we wrote, this is the load file. So I think I should bring up this one here. So this is the one that opens up the file, sucks in all the contents at once into one giant array, breaks apart the contents by looking for the new lines and turns them into null characters, then allocates space for this second array, and then connects each one of the pointers in the second array to the entries in the first array. And this works fine, and it's able to count the number of entries as it goes. But this one relies upon, first of all, loading the file in by getting the size of the file and then pulling it all into one giant string. And so it makes a picture that looks like this. Right? You've got one string here, and then a new line, and then another string, and then a new line, and another string, and a new line, and so forth. And then eventually we go through and replace these with nulls. And and then a second array that points to these. So some shortcomings of this is, well, I mean, for our purposes here, this is fine, but ultimately some shortcomings are, if you wanted to change one of these strings, like make it longer or shorter, you wouldn't be able to do that because you'd have to shift like everything down in order to make space for the new characters. Or if you wanted to delete some characters in here, you'd have to shift everything back in order to take up the space. And also, it relies on scanning through this larger array and looking for these new lines in order to count the number of entries that are in it. And that allows us to then know how big this array is supposed to be. But what if you could do all of this, first of all, not pulling in all the contents of the file all at once, and also be able to not have to know how many entries are in the file ahead of time in order to allocate this array? What if we could kind of do all of that at once and just grow things as necessary? So we can build a different data structure that it's got our file with lines in it. And so what it does is it starts out with this array that points to the strings. It reads in one line of this file, okay, allocates space for that, and then makes this point to that one. And then we read in the next line of the file, allocate space for that, put it here, make this one point to that one. Good so far? So every line is now in its own little chunk of memory rather than being this one giant piece. And then we come to this third line in the file. We allocate space for that, put the string into it, and then we go, uh-oh, there's no more space in this array. Let's make it bigger. And then point the next one. And then we just keep working our way through the file like that. Read in the next line, allocate space for it, put that line in there, make this one point to that one. And then we just grow this second array as we need it. And we also dynamically allocate all of these as we need it. So in Java, this is called like array list. It's an array that grows as you need it. In C++, it's like the vector class. And each one of these strings is now sitting in its own little chunk of memory rather than being in this giant chunk of memory here. Okay, so that's kind of what we're aiming for. So I think what I'm going to do is I'm going to kind of show you how that program is written. I'll actually write the program, but then it's up to you to take the pieces out of my video here and then drop it into your own assignment and make it work your way, or make it the way you want to write it. So let's call this like, I don't know, load file 3. And then let's just get started on this. So the whole point of this example program is going to be to show you how to make this array that gets bigger and bigger. In fact, why don't we just focus on that first? Why don't we just focus on an array that gets bigger and bigger as you put numbers into it, as you put values into it, and then we'll see how we can drop that into this loading the dictionary. Okay? So let's start by just having a program that just prompts the user to type in numbers, and it starts putting it into this array, and the array grows. Okay? So in this program, we are going to repeatedly prompt user for input numbers, add the numbers to an array of ints, grow the array as necessary. So we're going to have a loop in here. Let's have this loop, actually let's, now I'm thinking here, should I input numbers or should I input strings? I'll have it read in numbers, and let's say stop reading numbers when a negative number is inputted. So let's have a loop. Like this. Okay, so we'll print prompt. And then we'll get the input from the user. And now what we're going to do is start adding it to an array. So we need an array to put these numbers into. Because this is going to be a resizable array, we can't allocate it on the stack. The stack only holds fixed size arrays. So we need to use malloc to make a variable sized one. This is going to be just like the malloc you've seen before. Let's go integer pointer, let's call it ARR equals malloc. And then initially, this array is only going to hold, well, let's say it'll hold 10 integers. So we've now got our array that can hold 10, but we need to have an additional variable that keeps track of where in the array we are so that we can put it into the right slot. Let's call it, should I call it count? I guess so. And this is our current insert position in the array. Oh, maybe I'll call it CURR, current. Okay, so we prompt the user to input an integer. We actually get it from the user, and now we're going to put it in the array. Okay, and then when we're all done, we're just going to print out everything in the array. Now already I can see I've got a little problem here. What if I don't input 10 numbers? What if I only put 3 numbers in? I don't want to print out the entire array. I only want to print out the numbers that I actually inputted. So I shouldn't use 10 here. What I should use is the value of the current variable, which keeps track of, essentially keeps track of how many integers I put into the array. See that? So as I input numbers in the array, this, whoops, I didn't increment it. That would be a terrible thing. So as I input numbers into the array, this variable goes up and up and up. And so really by the end of the loop, it contains the number of entries in the array. So this shouldn't be 10, this should be the value of current. Okay, so let's give this a try. So let's do 5, 2, 9, 1, and then a negative number. 5, 2, 1, 9, negative 9. Oops, I don't actually want to input this negative 9 in there. So what do we got to do there? Say if input is less than 0, then break out of the array. Well, now that means I don't actually need this check down here because this will never actually get checked. So really I can turn this into a while true, an infinite loop. And then I'm going to break out when the input is less than 0. Okay, let's try this again. 5, 9, 1, 2, negative 9. That's what I wanted. 5, 9, 1, 2. Okay, we good so far on this? So just to recap here, I've got an array that can hold up to 10 integers, and I've got a variable that keeps track of, well, kind of keeps track of two things. It keeps track of where in the array we currently are inserting, and then when I get done with inserting, it's also going to contain the length of the array, the number of entries that are valid in the array. And then I've got a loop, and really I can just make this an infinite loop because I'm going to break out of the array when I encounter an input that's less than 0. Any other input is added to the array, and then this variable is incremented. And then finally, when I'm done with the loop, I'm just going to print out the whole contents of the array. But of course, this program has a problem when I reach the capacity of the array. When I reach 10 elements, I'm not able to insert anymore. In fact, the program might crash as I continue to insert elements because it just goes off the end of the array. So what I want to do is when I reach the capacity, I want to make that array bigger. So I need to do two things. First, I need to detect when that happens. And the second thing is make it bigger. So how do I know when this happens? Well, when the value of current reaches 10, then I know I've reached the capacity of the array. So let's see, we'll get the input from the user, and we'll check to see if it's a negative number. And then what we'll do here is extend if necessary. We'll check if the value of current is greater than or equal to 10, then we know that we've exceeded the capacity and we need to make it longer. So we're going to use a function called realloc. In this function, you pass it two parameters. For malloc, you only pass it one parameter, which is the number of bytes you want to allocate. For reallocate, you pass it two parameters. You pass it the pointer to the array that you want to extend, and then you also pass it the new capacity, the new size that you want to make it. So it's not going to be the number of elements that you want to add to the array. It's going to be the new size. So if it was currently 10, and we want to add 10 more to it, we now have to pass in 20. And then it returns to us the pointer to the chunk of memory that it just extended. So we really just assign it back to itself. Okay, so that's how you use realloc, but we've got this additional problem, and that is, what if we get to 20? How do we make it bigger then? So we can't put in these like fixed numbers here. We need to put in a variable that keeps track of the current capacity of the array, and then we're able to extend that as we go. So let's make a variable called capacity, and we'll set its value to 10, and then we'll take out all the places where we had 10 or 20 and put in this variable. And now here, instead of 20, we're going to make capacity increment by 10, and then put in the new capacity. So now, as we fill numbers up, it's going to grow in not multiples, it's going to grow by 10 elements each. So let's start putting numbers in. 5, 2, 3, 1, 9, 10, right? You can just keep putting numbers in, and it will just keep going. And then finally, when I put in a negative number, it's done. And here I can show that I was able to put in a total of 35 numbers and no crashes, and the array is just getting longer and longer. So this is the general recipe you're going to use here. You're going to set an initial capacity. You're going to malloc the amount of memory equal to that capacity times the size of each element of the array. You're also going to have another variable that keeps track of where in the array you currently are. And then you're going to start filling up the array. And if the current value of the current element of the array is equal to the capacity, then increment the capacity, reallocate the array, and then just keep going. So this is basically how ArrayList works in Java. Also the vector class in C++ is it's got this current capacity of the array. It's got a counter that tells you where in the array you currently are, and then when that counter reaches the capacity, it makes the array longer. Now in Java, it's actually a little more complicated. In Java, there's no way to extend an existing array. What you have to do, really, is create a new array, copy all the values from the old array into the new array, and then throw away the old one. What C is doing here is it has allocated a chunk of memory for the original array, and then if it detects that there's nothing following that array, it'll just simply move the end marker out further and make the existing array longer. But if there is something after the array, then it will go ahead and create a new array, copy the values over, and throw away the old one. And this all happens completely transparently to use. Whether it makes the first decision to simply extend the existing one, or the second decision to create a new one and then throw away the old one, is completely invisible to you. You don't have to worry about that. And so that's why realloc returns to you the address of the same array, because it may have elected to create a new array. And so it needs to give that new address back to you. Okay, so I know I kind of blew through that quickly, but I wanted to show you how reallocate is used. Any questions about that? No? Okay, so let's see how we can use that information to then build this data structure that I was talking about. I think what I'm going to do is I'm going to make a copy of this. I'm going to call this array extend, just so I've got a separate file that contains that code. Okay, so let's gut this thing. Let's pull this out. Okay, so now we are going to repeatedly prompt the user to input strings, add the strings to an array of strings, grow the array as necessary, stop reading strings when the word done is inputted. Okay, so it's basically the same program, but now it's not going to be integers, now it's going to be strings. So what we had before was a single array that we put numbers into. And then when the capacity is reached, we extend the array, and then we're able to add more numbers. But that's not what we're going to build here. What we're going to build is an array of strings. Okay, so let's start out with an array of strings that can hold up to 10 strings. Actually, why don't we make it 5 for now, just so that it grows it more frequently. So we've got int capacity. Let's make it 5 to begin with. And then we're going to make our array of strings. So this is an array of character pointers. So this first element is going to be a character pointer. It's going to go off and point to some string somewhere. And the second one is also going to be a character pointer. And the third one's also going to be a character pointer. So when we call malloc to allocate this array, it's going to hand back the address of this thing. And we're going to put it into a variable. Let's call it ARR. But what type is that?
That's a pointer to a character pointer.
Yeah. So this pointer right here is pointing to one of these things. And one of these things is a character pointer because it's pointing to a string. So its type is character pointer pointer. So we'll go character pointer pointer array equals malloc capacity times size of, and then what do we put inside the parentheses there?
That'll be character pointer.
Yeah. So by the way, if you're still confused about this malloc recipe that I'm showing you, let me give you a little hint here. So if you wanted to make an array of integers with 10 elements on it, here's how you would allocate that array on the stack as a local variable. If you wanted to use malloc, you would say int pointer array equals malloc 10 times size of int. So the thing I wanted to show you there is whatever you put out in the front, that goes there. And it also goes there. Okay? And then whatever you put inside the parentheses goes there. And then whatever you chose for the name of the variable goes there. Let's say you wanted to make an array of floats. Well, following the same recipe, this float goes out in front. The name of the variable goes after it. And then you also put in this star to say that it's a pointer. And then equals malloc. The 20 goes right there. Then you put a times size of, and then whatever you put on the front float goes right there. So let's say you wanted to make an array of strings. You would have said character pointer names 10. So this is an array of 10 character pointers. So following the recipe, you would put whatever this is out in front. You'd add an additional star. Then the name of the variable equals malloc. The size, which is 10, times size of, and then whatever this is, put it over there. So I just used the same recipe 3 different ways, and you can see how all the pieces just fall into that malloc statement. Okay, so coming back over here, this is exactly what I just wrote. Character pointer pointer array equals malloc capacity, which was the 10 in my example, times the size of character pointer. And then I need to have that current, like I did before.
When you call malloc like that, do you have to cast it to the correct pointer type?
In older versions of C, you did. In the latest C11, you don't. The older versions of C actually, I think, they may have had malloc actually return a character pointer because that was the closest you could get to just like a generic address. And then you had to cast it to the right type. But in the newer ones, it's defined to return a void pointer. And a void pointer is just a generic pointer, and it automatically casts itself to be whatever the correct thing is.
Okay, thank you.
Okay, so now we're going to go into our loop. Just like before, we'll make this an infinite loop. So while 1, that's always true. We're going to get input, we're going to prompt the user, and then check to see if it's the word done, and if it's the word done, we're going to bail out. So that means we're going to need an array, we're going to need a string to hold the user's input. Just like before, when we did extend array, where is that? Where did my file go? Oh, array extend. It's way here. Just like before, I had this variable called input to hold the current input for the user. Here I'm going to have a string that holds the current input. And I need to make it long enough to hold whatever the user might type in. Let's make it 100. Okay, now we're going to prompt the user. And let's use fgetS here, because I might want to type in a string that contains spaces. And since I'm using fgetS, I'm also going to want to just trim off those new line characters, right? And since I'm now using string functions, I'm going to need to include the string library or the string headers. Okay, so put in some comments here. Prompt user to enter a string, end on done. Okay. Trim new line. And now we can check to see what they typed in. If string compare input and the word done is equal to 0, then break. We're done with the loop. If they didn't type in the word done, we're going to go ahead and add it to the array. Okay, so we've got our initial array that can hold 5 pointers. And do I have my capacity of 5? Yes, I do. Good. And I've got a variable called, what did I call it? ARR? Yep. That points to that thing. And then currently, each one of these things here is a null. Actually, they're just garbage values. They don't point to anything in particular. And I have my user's input in a variable called line. Oh, not line, input. And so the user has now filled that in with a string that ends in a null character. So the next thing I need to do is make this entry point to that thing. So how do I do that? ARR bracket current, which is 0, is equal to input. So the array called input, the address of it is going to be put into my array. And then I need to increment this. Oh, I also need to do that check. If current is greater than or equal to capacity, then I need to extend the array. And we do it just like we did before. Make the capacity larger, and then call realloc with our new capacity times the size of character pointer. So you can see how this program pretty much mirrors what we were doing in the number program, but it's now working with strings. You can see this statement to reallocate looks almost identical. Oh, except that I need to pass in array here. Okay, what happened here? Oh, I see. So this is strings. There we go. All right, let's type in some strings. Let's put in Monday, Tuesday, Wednesday, Thursday, Friday. So at this point, I've typed in 5 strings, And now it should be going on to my 6th string. And in fact, I might want to put in here a little printf that says extending array, just to let me know that this is happening. Let's try that again. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, extending array, Sunday, and now done. Uh-oh. That didn't look so good. What happened there? What happened to all my days of the week?
So it looked to me like you were on line 34, you're setting the current index of the array to input, but input's scope is that while block.
Okay.
Oh.
So you're right there in that when I come into this bottom loop here, essentially the scope of input is gone. But remember, when you drop out of scope, it doesn't actually erase the contents. They're still there. They're still in memory. So essentially, each element of this array is pointing to a string that's still in memory, but not in use anymore. So there is a slight problem there in that if I was doing more inside of my loop, that string might get overwritten by some other variable. So there is that danger, but it's not happening because I'm not doing anything else other than just stuffing the array full of strings. But Akash on YouTube says the value of input is getting overridden every single time. So what happens is, as I enter my strings here, so the first thing I type in is Monday, and then I make this one point to that. And then I type in Tuesday, and I make this one point to that. And then Wednesday, I make it point to that. Thursday, I make it point to that. Friday, I make it point to that. And then finally, I type in done. And all these elements of the array are pointing to that one input string, which now just contains the word done. So that's what's happening there, is I'm reusing that same array over and over again, overwriting its values. And every element of this sort of parent array is pointing to that one input string that's getting overwritten every single time. So all the elements are pointing to the same string. And that's not what we want to do at all, right? We want to preserve those lines of input, which means we need to set them aside into their own strings that persist beyond every line that's being inputted. Okay, so how do we do that?
Can we use malloc to assign a memory space for it?
Yeah, so we're going to get a line of input from the user. We get a line of input from the user, and then we'll malloc some space for that string and then copy that input into that string. Now, we can't malloc it first and they get input directly into that string because we don't know how much space to set aside. We could set aside 100 characters, but our goal here is to make this data structure use kind of like as little memory as possible. So I don't want to set aside 100 characters for every string and only use 5 of them each time. I'm going to use one line of input that can hold up to 100, get that input, and then I can count the number of characters in it, and then malloc just that space, just enough space for it. So if I type in 5 characters, it uses 5. If I type in 10 characters, it uses 10. If I type in all 100, it'll use 100, but now I'm using just as little space as possible. Okay, so we're not just going to make this array point to input. We're going to set aside a new string to hold the inputted value, copy the values over, and then make the array point to that thing. So let's go character pointer new string equals malloc. Then how many characters do we have to set aside?
Just the string length. Do we have to add 1 for the null?
Very good. We do have to add 1 for the null, right? Because the string length, if I type in Monday, is going to be 6. But I need 1 more to hold that null character. And that's really important, really, really important. Because if you don't do that, then every single string ends up overrunning itself by 1 character. Your program could crash, or worse yet, it starts overwriting the next string that it mallocs. It's also really important to put the +1 in the correct spot. If I put it here, what does that do? Well, it calculates the length of a string, but starting 1 character in from the beginning of the string. So it's always going to undercount by 1 character. So you want to put it out here. And then you're going to multiply by the size of a character. Okay, but this is still not correct. Because order of operations says that it's going to take the size of the character and multiply that by 1, and then add that to the string length of input. So I need to put an additional set of parentheses around it to make sure that I'm doing the addition before I do the multiplication. So there's one question here, which is, if I have this declaration of a string that's inside of this loop, don't I get a new one every single time? And the answer is no. Essentially when the variable falls out of scope, which it does temporarily when we drop out of the loop and then go back and start the loop over again, the compiler sees that you're just recreating another variable with the same name, and so it recycles the same memory locations. So if you're using the same variable name over and over again inside of a loop, it just recycles it over again. It doesn't create a brand new one every single time. So in other words, when a variable falls out of scope, the compiler sees that that variable's memory is now up for reuse, and then when you come back into the loop again, it just recycles that same memory location. Then another question is, why do we have to use this input string at all? Why can't we just use this new string that I've allocated? Well, the answer there is I don't know how long the user input's going to be. If the user only types in 5 characters, I want this array to be exactly 5. And if the user types in 100 characters, I want it to be 100. But I have to allocate the input array before they've typed anything in. So I'm using this little trick where I've got, I hate using the word trick, I'm using this technique where I've got one temporary array, one temporary string that holds the user input, and then I'm going to copy that into the actual string that's going to hold that input, but it's just as big as it needs to be. So I'm not wasting any space. Okay, so I've allocated space for the string. Now I need to do a copy. And when I do the string copy, it's going to stop when it hits the null character. So even though the input string can hold up to 100 characters, the string copy is going to stop when it hits the end of the actual input. Oh, I see what you're saying is like you're using a guess of 100 up here, why not use malloc for that and then reallocate it to be the correct size later on? You know, that might not be a bad thing to do. Although alloc and realloc are kind of an expensive operation to do in the first place. So when you do a realloc, you know, you're actually diving into the whole memory management library. So I don't know. I don't think it makes a huge difference for this particular program, honestly. Okay, so I made a copy of the string, and now I'm going to make this be the new string. So I should get a brand new string every time I get a line of input from the user. All right, let's try this one. And then there we go. We got them all. So now we've made a picture that has every single one of these strings occupying their own little spot in memory. So now, after we've done that, we can then search through this array pretty easily just using the string compare function to go and find strings that we're looking for. Okay, so that's basically how to create an array of strings and have that array grow as necessary so that we waste as little space as possible. So just to recap, we've got an initial capacity of 5. We're going to allocate this array that holds initially 5, although we're not going to use all 5 initially, we're just going to use 1. And in fact, you might be asking, why don't we make the initial capacity be 1 and then increase the capacity by 1 every single time? Why are we jumping up by 5s? And the answer there is, again, every time you call malloc or realloc, you're diving into the memory management library, and that's like computationally expensive to do. If you incremented the array by 1 every single time, and then you call, and then remember I said when you call reallocate, it'll either extend the array if it's possible to do so, or it'll create a new array and copy everything over. Well, in this version of the program, I'm calling malloc quite a bit. Every single line of input gets its own memory set aside. So although the picture looks like this internally, it may actually look like well, let's say green is my little array of strings, and then I create a string to hold one of my inputted strings, and then of course this one points to that. And then now let's say I want to extend the array by 1. Well, I can't do that because now there's another chunk sitting right behind it. So I need to make a new array that can hold now 2 things, copy this stuff over, throw this one away, allocate my new string, and then make this point to that one. Okay? And now I've inputted my third thing. There's now no space to make this one bigger, so I have to make a new one, make this one point over here, make this one point here, throw this one away, allocate my new string, make this one point there. So if I only increment it by 1 each time, I'm like all the time going to be running out of space to make that thing bigger, and so I will have to make a new one and copy the values over. So by making it jump up by 5s, it's only going to have to do this allocate and copy once every 5 elements. And in fact, I could make the capacity even larger. I could make this initially perhaps 10 and make it extend by 10, and now I only have to do this every 10th allocation. The array list implementation in Java takes it a little step further. It actually increases it by 50% each time. So it starts out with 10, and then it goes up to 15, and then like 22, and then 33, right? So it increases by 50%, 150% each time. So it makes it 150% as big each time. And so the idea there is, if you're going to make a large array, you're going to add a whole bunch of things to the array, chances are you're going to be adding a whole bunch more things to the array. So you might as well make it like go up not in fixed increments, but increments that are proportional to the size of the array. Some implementations could even double the length of the array each time, although I would actually recommend against doubling it, strictly doubling it, because if your array, let's say, has 1 million entries into it, if you double it, now it's going to be 2 million, and then it'll go to 4 million, and then 8 million, and then 16 million. And when you double it, you know, I would say you're probably going to end up wasting a lot of space. Yeah, so I think 1.5 is a pretty good compromise. But we'll go with plus 10. It's fine for us. We're not adding a whole bunch of things to the array. Okay, so back to my recap here. So we've got our initial capacity of here 10. We allocate the array one time at the front of the array to make it the initial capacity. And then we get a line of input from the user, strip off the new line character, check to see if the input is done, and if it is, break out of the loop. Then, if we've reached the capacity, extend the array by adding 10 to the capacity and then calling reallocate with our new capacity. Then, once we've done that, we allocate space for a copy of the string, and we use just enough space, just the space that we need, which is the length of the string plus 1 to hold the null character. Copy the string over, and then add that string to the array. Finally, we increment the counter so that we go to the next element of the array. And then when we're all done, we just print out the array. All right, so we're jumping up by 10s here so that we don't end up calling reallocate too often. We can't get away with calling it, we can't get away with not calling it at all, but we want to kind of minimize the number of times we call it because the memory management routines are actually fairly complicated. Okay, so given this information, can you now work on this assignment? So in this assignment, I will give you a Bitbucket repository that you can clone into your own directory. Here's the address of it right here. And I'll give you some starter files. Let's go take a look at them. So here are the files. There's dictionary.c, dictionary.h, and then a main. So there's really two files here. Main just calls load dictionary. And then it goes into a section where it asks for a word to search for, trims off the new line, breaks out the loop when you type in done, and then searches the dictionary. Now, load dictionary is using that same technique that I mentioned a few weeks ago, where we need to pass back two things. We need to pass back the array of strings and how long that array is. But we can only pass back one thing. So load dictionary passes back to you as its return value the address of the array, And it also gives back the length, but it does it by filling in an integer that you pass to it. So here's dictionary. Load dictionary takes in a file name to load. And here's that size pointer that we're going to fill in. And here's the array of strings that we're going to pass back. Open the file for reading. And then here's what you need to do. You need to allocate memory for an array of strings. Read the dictionary line by line. Expand the array if necessary using reallocate. Allocate memory for the string that you just inputted. Copy each line into the string using string copy, and then attach that string to the array. Break out of the loop when you are done reading the file. So you're not going to use that done technique that I showed you in the previous program. You're going to be using when fgetS returns a null to you to indicate that it reached the end of the file. And then finally, you need to change this line here. You need to change this so that the size variable reflects the actual size of the array. And then finally, return a pointer to the array of strings. And then here is a function called search dictionary, and this one here is already complete and works for you. Already works. You pass in the target string you're looking for, the array of strings, and its size. And then it just simply does a linear search. It searches through the dictionary looking for the target word, and then returns it if it found it. Okay, so this brief little assignment here just takes the concepts that we learned from the program that I wrote over the last half an hour or so, and it's really just a short program just to get used to the idea of calling malloc and calling reallocate to make the array bigger. Let me copy and paste into the chat the address of this repository. Let me know if that does not work for you. Looks good? Okay, we got a confirmation that that link works well. Good. Okay, let's move on to something a little bit different. So what I think is going to happen here, since I had forgotten to talk about that assignment earlier, is that's basically going to be your assignment for this weekend, is to work on that, loading that dictionary. And then we'll get on to, cracking the passwords quickly next week. So I'm going to try to cover as much as I can today, and then we'll see how far we get. So my son is into Pokemon, right? So he collects the cards. He doesn't play the game. He just collects the cards because he thinks they're cool. And if you're not familiar with this card game, with this cartoon, you've got, things like come on, focus there. You got like the name of the Pokemon. You've got hit points, and then somewhere in here also is like the type of Pokemon, which I think is. This is all a mystery to me, right? But it's like fire and water and Chris is smiling because you've probably gone through this, right?
Yeah, my kids do the same thing. They have those binders with all the cards,
Yeah.
and they seem to know all about them, and I know nothing.
Yeah. So it's like something about the the background of the card indicates what type of Pokemon it is. So I guess those of you who are listening here, what are the attributes of a Pokemon? Well, there's many, but what are the important ones? Right, you've got the name of the Pokemon, and you've got its hit points, and you've got its type, which could be earth, water. What are the other types? Does anyone know? I don't know. I'm going to have to Google this, right? Because I really don't know. There we go. Electric. Grass. Fire, and so forth, right? There's a whole bunch of them. So we can make a structure, a struct in C to reflect this. So I'll define a struct called Pokemon, and in there I'll put in those 3 fields. I've got character name, and let's set aside maybe 20 characters for that. You've got its hit points, and we've got its type. And maybe, I don't know, 10 characters for that. And I could use something called an enum for the type, but I'll just stick with a string for now. So let's create a file that contains some Pokemon. So I'll just grab them right off of the cards that I've got here. I'll just pick up random ones. Of course, there's a Pikachu, right? And let me see if I can find one. Actually, we'll just guess what the hit points are. Let's just say the hit points is 80, and Pikachu is a electric. And then I've got here a Kadabra. Hit points is 60, and I'm guessing this is a, I don't know what kind this is. It's got a purple background. I'm not sure what that means. What does that mean? Purple. It's a purple Pokemon. Well, let's just say that's Earth. I don't know what it is, but we'll go with that. Someone's going to write to me and go, you're all wrong about that. Put in some more. A Grubbin, 60 hit points. We'll say this is grass also. Whalmer, 120. This is clearly a water. The why not? Why not? 50. And let's say this one here is Earth. Rapidash. And we'll say this one is Fire. Oh, and there's of course Charmander. 50, Fire. Okay, so let's make a new file. Let's call this Pokemon.c. And so in this file, we'll define that struct that we just came up with. Struct Pokemon. Character name 20 for that one. Hit points is an integer, and a type is a string, and we'll make 10 characters for that. Don't forget the semicolon. This is one of the few places in C where you'll see a semicolon at the end of a brace. Okay, so let's have it read in these Pokemons from a file. And I've made this file be a comma separated file, so I can use something like scanf to read in these strings and numbers and put them into their individual pieces. So let's open up that file. File pointer P equals fopen. Pokemon.txt for reading, and let's just check to make sure that we actually were able to open it. And exit if we weren't able to. So now, while fgetS line from P is not equal to null, so we're going to get a line of input from the file. Now that we got a line of input, let's break it apart into its individual pieces. So we'll use scanf to read from that line. So the normal scanf reads from the keyboard, but scanf can be used to break apart a string into its individual pieces. And then we got %s, comma, %s, oops, %d, comma, %s. Actually, and let's see, should I? No, I think that's fine. And then we're going to read that into an array of these things. So we need an array of Pokemon to hold them all. Got to collect them all, right? So how do we make an array of Pokemons? Well, we make the array just like we do any other array, except the type here is called struct Pokemon. It's a two-word type. And let's call it Pokemons. And although I know that I've got 8 of them here, let's just make the array hold 10. And an additional variable to keep track of where in the array we currently are. Okay, so we read in a line of input from the user or from the file, then we're going to break it apart into a string, a number, and a string, and we're going to put that right into our array. And we'll do it like this. Pokemons sub current, which is the how far into the array of Pokemons we are, dot name Pokemon's current dot hit points, but because this is an integer, we need to put the ampersand in front of it. And then finally, Pokemon's current dot type. And that should be it.
So when you initialize that array of Pokemons, does it actually fill that array with structures ready to use?
Yeah, but they're all contain garbage values.
Okay.
But yes. So what we end up with is let's call this Pokemons. And each one of these contains, 3 little boxes. Does that make sense? Right, where this first box is the name, this is the hit points, and this is the type. And latest comment here is, we're reading directly. Couldn't we overrun the array if the file has too many Pokemons? Yes, we could. But there's a way around that, isn't there? If only there was a way to make the array bigger when I had to. Anyway, we'll press on. Because my point here is not to show you how to do that. My point is to show you that we can read values out of a file and put them into a structure. Okay, so once we get done reading from the file, we can then close that file. And then we'll go ahead and print them out.
Oh, we can't see your screen.
Oh, sorry. Oh, and someone else is asking, since we're using scanf here, what happens if the name of the Pokemon is too long? You're right, and that is also a problem. However, you can do something like, I could pass in a 20 here and a 10 here, which would ensure that I can only read up to 20 characters in this string and up to 10 characters in this string. But then if the string is too long, if the name is too long, then this whole thing falls apart, because then it's not able to read in the next number, and then therefore it won't read in the next string, and it will just like completely collapse. So again, my point here is to illustrate the idea of reading values into a structure, and I'm avoiding for this moment here all the kind of like the safety of exceeding the length of the strings. So we're not going to worry about that at this point. Okay, let's go ahead and try this out. It looks close. There's some weird stuff going on here. First of all, I can see that the commas aren't gone. When I did the scanf up here, I was putting the commas in as part of the pattern, and it should throw away the commas. Any characters that are outside of the percent tags should get discarded, and they're not getting discarded. And also I've got these weird numbers and characters over here. So what's going on? Well, it has to do with the way %s works. See, %s will read in characters and it will stop when it hits the first space. But I don't have any spaces on my strings, on my lines. So it's reading in the entire string, the entire line, as the name of the Pokemon. And then whatever's left over are just these junky values. So I need an alternative way to read in these strings, but stop at the first comma instead of at the first space. And so there is another way to do this in scanf. It's not with %s, it's with % and then brackets. And then inside the brackets, and if you've used things like regular expressions, you might kind of recognize this as being, this is a set of characters that I will allow in my string. But what I'm going to say here is I'm going to allow any character except a comma. So the caret and then a comma means any character except a comma will be part of my string. And then I'll read in the comma, and then number, and then a comma, and then again. And then I can use %s for the remaining because that'll stop when it hits the end of the line. Okay, so this here is a way to read in a string, but stop at the first comma. So a couple of people are commenting exactly what I just talked about. They're on a 10-second delay, so I talk about it and then they respond because they heard about it 10 seconds later. All right, so let's give that one a try. There, that is much better. The commas are now gone, and the names of the Pokemon are now sitting in front of the colon, which is what I had in my print statement, and their hit points and types are sitting after the colon. So last time, we talked about sorting an array of numbers. And we use that qsort function to do that. But now I want to sort these Pokemon by something else. They're not just numbers. These are now structures. So if I want to alphabetize them, I need to sort them by their name. Or if I wanted to put them in order by their hit points, I would have to sort them by that field. How can we adapt the qsort function to work with a structure instead of just integers? That's what we're going to do today. But I can see it's almost 11 o'clock, so I want to give you a chance to take a little break, get up, stretch, grab something to drink, and then I'll come back and show that to you. Okay? So I'm going to pause the Zoom recording, and we'll be back in about 10 minutes.
Recording stopped.
Okay, and I can't pause the YouTube recording, so we'll just keep going there. Let's catch up on some of these comments. We once saw a YouTube video of a guy who stored the data as a binary file and then read it in, and they magically became a struct type array. So yes, you can do that. You can So this is kind of an advanced topic here. There's a couple ways to do that. One would be you could open a file for writing, but open it as a binary file, and then just simply print the structures directly into that file. So it would go in as the binary values rather than textual values. And then when you read it back in, it just reads it right back in as the binary values. So actually, I don't think you're doing that as writing it as a binary file. What you're doing is you can do something called memmap. M-E-M-M-A-P. And you can basically say, take this chunk of memory, which you allocated, I think, with malloc, and then make a mirror of it on the disk. So the file on the disk is an exact byte-by-byte mirror of what's in the allocated memory. So when you close that file, it just now has in the file a copy of what was in the memory. So when you open the file again, and this time you don't use fopen, again you use memmap. So you allocate that chunk of memory, you map it to that file, and then boom, that file is now populated with the content, or that memory is now populated with the contents of the file. I think that's probably what that fellow was doing on the YouTube video, was using memmap. But again, that's kind of a more advanced topic. But it is really cool. The problem with using memmap is that if you're building a data structure, like you're building, let's say, a linked list, where the contents of the array might contain pointers to other array locations, that's not going to work so well, because when you read the file back in, when you remap that file back into memory, well, that depends upon the addresses in the malloc memory being the same as what was in that file, and they may not be the same. When you allocate this new chunk of memory to map the file into, you may get a different address range. So you got to do something about that, where you have to go back and fix those memory addresses, and that takes a little more work to do. So, or you'd have to somehow store the data on in the memory, but instead of using pointers that point to memory locations, it'd have to be something more generic, like point to index locations rather than memory locations. Then it would work. Does memmap use lazy loading? I think it does. So it basically maps the file to memory, but it doesn't read the whole contents of the file in all at once. Only when you access that memory location does it go and fetch that data from the disk and then populate it in a memory. So this could potentially be a way to map a huge chunk of memory onto a file, but then load it on demand. So it's really pretty cool what it does. Next question is, when we do the sort, can we just make the compare function compare just a single field of the struct? And that's exactly what we're going to do. You got it right. So I wish I had more time to talk about mmap, but we only have 16 weeks here. If only I had like an advanced system programming, but that's more like an upper division course, or it's more specialized, right? Our point is not to turn students into C programmers or embedded systems programmers. It's to help them become computer scientists and transfer over to a four-year institution. So doing stuff that's particular to a particular operating system or particular dialect of C is great information to know, but maybe not appropriate for an introductory course like this. There was a time, I'd say 20, 25 years ago, when we had at our university, our college, a lot of specialized courses. We had courses in system administration and internet server administration, like running a web server, running a mail server, DNS server, some we had lots of really specialized courses. And that was from a time when somebody could get a few courses under their belt. And this is during the dot-com boom of the mid-90s to the early 2000s. You could get a few courses, learn a few skills, and then go and pick up a job that paid $100,000 or more. I mean, all you basically had to do was breathe and know a few skills, and you could get a job like that. It was great, but it was very short-lived, right? As soon as that dot-com bust happened in the early 2000s, companies went back to saying, well, you know a few courses, but now you're just what you might call a one-trick pony, right? You just know how to do that one thing, and that doesn't make you super valuable as an employee. So most employers, at least in the United States these days, require someone who's a programmer to have a bachelor's degree in computer science. And that means getting a broad education across a wide variety of fields or subfields within computer science. And then when you move into your job, you'll learn the specifics for what you need for that particular job. So if you move into a job where you are doing embedded systems programming or systems programming, then you'll pick up the C skills or the C++ skills you need to become a better embedded systems programmer. But if you work into web programming, you probably don't need to do this mmap stuff at all. You're probably better off learning about databases and style sheets and jQuery and JavaScript stuff. So the whole point really of a bachelor's degree in computer science is to give you a broad foundation in a whole bunch of topics in computer science, not a specialization in any one area, and then you pick up what you need to know as you move into a particular job. At least that's the way it is in the United States. It is kind of a shame, actually, that there aren't more computer science positions that are just strictly what we call a coder. Like someone's job is just to take a program specification and turn that into a working program. And I would say you don't really need a 4-year bachelor's degree to be able to do that. You just need a lot of programming experience. And so I personally think there would be, or there could be, room for a 2-year or vocational type position where your job really is just to, again, take a working program specification and turn that into a program. So somebody else does the job of architecting and designing the program, and then you just take that and turn it into code. For that, you don't necessarily need a bachelor's degree, but you should probably get like a 2-year degree. And so I think that would be a place where we could do lots of specialized courses, right? You want to become a system programmer in C++, we could offer you Introduction to C or C++, and then more advanced things where you learn about the system library a bit more. But that's just not the nature of the computer science field in the United States at this point. So pretty much any occupation involving computer programming, like where that's your core competency, it's going to require a 4-year degree, at least in the United States.
Recording in progress.
Okay, we're back from our break, and we have now written a program to read a bunch of Pokemon in from a file, and now we want to sort this so that we can display them maybe alphabetically or sorted by their hit points or whatever you want. So I think I'm going to make one change to my program here, and that's I've got this variable called current, which while I was reading in the Pokemons contains the current index into the array. But really what I want this to reflect is once I'm outside the loop, it reflects the length of the array. It's true, I can hold up to 10 Pokemon, but only 8 of them are actually valid because that's how many are in my file. I've got 8 of them here, but my array of Pokemon up here holds 10. So this current variable should reflect the number of actual valid entries in the array, not its total length. So I'm going to make another array or another variable called length, and it's going to be just a copy of the current. Now I can say length here, and I feel better about that. And alternatively, I could have used length up here. I could have made this length and this length and this length. I could make all of these length, or I could have called it size or something like that. And and a more experienced programmer would see, oh, what you're doing here is you're incrementing the size as you go through the array. That's fine. And now I know that when I get to the end of the loop, that variable contains the number of elements in the array. Fine. But here I'll just make another variable whose value is just a copy of current. Okay, so now that we've got the Pokemon printed out, I now want to sort them. So let's say I want to sort them by their, let's do by their, what should we do? Should we do by their name or by their hit points? Take a pick. We'll actually do both, but which one do you want to do first? If you don't have an opinion, I will flip a coin. Heads, do it by hit points. Tails, we do it by name. I should have written a program to do this. Oh, somebody finally said, do it by name. Okay, we're doing it by name. All right. So we're going to call qsort. We're going to sort the Pokemon's array. The next parameter is how many elements in the array. The total number of elements is 10, but we only want to sort the first 8 of them. And that's sitting in this variable called length. Oh, it sounds like it's a unanimous decision to sort them by name. Okay, we'll do that. Third parameter, how big is each one of the elements of the array? Tell me what I should type there. So we've got this array of Pokemons. Each one of these elements holds a Pokemon. So what do I put here to tell me how big each Pokemon is?
Is it size of the Pokemon struct?
Yeah, size of struct Pokemon. And then finally, the name of a function that is going to be used as my comparison function. I'm going to call this by name. So it's a carefully constructed name that sort of reflects what it's going to do. So I'm going to sort the Pokemons by name. Or yeah, I could call it Pokemon sort by name. Something like that. Something that suggests what it actually does. Okay, so here we are inside of this comparison function, and when the sort is happening, remember it's going to have A points to one of these Pokemons and B points to one of these Pokemons. So it comes into my function as a void pointer, but what is it actually? What are A and B actually pointing to?
They're pointers to Pokemon structs.
Yeah. So I gotta go struct Pokemon pointer A equals a cast. Oh, I'm going to call this AA. And struct Pokemon pointer BB equals struct Pokemon pointer B as a cast. And so now I want to do a string compare. Remember, string compare already returns the kind of values we want, either 0, a negative number, or a positive number. So I'm just going to return whatever string compare returns. But what do I pass in here? Remember, AA is a pointer to a struct Pokemon, and BB is a pointer to a struct Pokemon. But I want to look at the name field within each one. So I've got AA points to, actually I don't have to draw this picture. I can just do it like this, AA and BB. So AA points to one of these things here, but I want to pass string compare just the name field within it. So I need to dereference the pointer and then send it to look at the name field. I need to dereference the pointer and send it to look at the name field. And the reason why I put the star inside of parentheses is because if I had typed in AA.name and then put the star in front, the dereference operator has a very low order of precedence. It's very low on the list. So what this would actually be interpreted as is trying to actually dereference the name pointer. But I don't want it to do that. I want it to dereference the AA pointer. So I need to put that in parentheses first. Okay, that's my function. Let's give it a try. And there we go. You can see they are now sorted by name. Very nice. So what if I wanted to sort them by hit points? Let's make a function called by hit points. Remember, I said I was going to do both of them eventually. We'll do the cast just like we did up here. And then we'll say return dereference AA dot hit points minus dereference BB dot hit points. When we subtract those two values, because they're integers, if they're equal, then you'll get 0 as a result of subtraction. And then if AA is smaller than BB, or if the hit points for AA is smaller than the hit points for BB, then we'll get a negative number, which is exactly what we wanted. Now we can just sort them by hit points. Oh, I made a mistake somewhere here. What did I do?
On line 20, your first parameter is also called B.
Oh, there we
Should
go.
be A.
Thank you. Ah, good. That fixed it all. Okay, and now they are sorted by hit points. So we can sort this array by any one of those fields just by creating a different function and then passing that function in depending on how we want to sort them.
Can I ask a question about where you're dereferencing the pointers?
Yep.
I've seen some mention of using an arrow notation
Yeah.
with
So
struct pointers without having to dereference them.
yep. So the this particular construct of dereferencing a pointer to a struct and then accessing an element within that struct is so common, there is a special syntax just for that. So it uses an arrow, which is constructed out of a dash and a greater than sign. And this notation, using the arrow, and this notation, using the star and the dot, are completely identical to each other. This is called syntactic sugar. This is an actual term. It's like a piece of syntax in a programming language that's just there as a shortcut for something else. It's there to make the programmer's job easier. It does not confer any advantage otherwise. It's not faster, it's not slower. They are 100% identical to each other. In fact, anytime the compiler sees this arrow, it just turns it into this behind the scenes.
All right, thank you. That was helpful.
Yeah, the people on YouTube chat were like, what about the arrow? What about the arrow? So they've been actually talking about this for the past 5 minutes. And so I'm glad you asked that question because I was going to get there eventually. But yeah, so the dereferencing a pointer to a structure and then accessing an element of it is such a common thing to do in C when you're starting to deal with more complex data structures that there's a piece of syntax just to do that. So you might recognize the dot notation from Java or C, or not C, from C++ or Java. And so really, actually, in Java, the arrow is equivalent to the dot. So the dot in Java, I should reverse that around. The dot in Java is equivalent to the arrow in C because every object is really just an address of an object. And when you access the fields of an object, you're really dereferencing the address and then going to that field. Okay, so let's switch that around. Let's make this AA pointer. You actually pronounce that arrow as pointer. So you say AA pointer name and then BB pointer name. Oops, I'm still sorting by hit points. Let me sort by name instead. There you go. All good. And so the question is, can we get away with not doing these casts? And no, I've not found a way to get away from that. However, you could put the casts in here. It just makes this messier. You could do something like struct Pokemon pointer A, and then instead of parentheses to make sure we do the cast correctly. It just gets ugly, right? So I'd rather just make a new variable that contains the result, that contains the cast up here. This isn't actually, honestly, not any slower to put the casts down here instead of up here. You might be thinking, well, I'm creating a new variable, aren't I, right? Doesn't that require more memory? You know, once the optimizer takes over, it'll see that you create this variable, but you don't ever actually alter it other than just assigning to it the first time. and it'll effectively just get rid of that variable. It will just wash it away and say, you don't really need that variable. So I guess the upshot there is there's really no downside to creating extra variables. Once the optimizer takes over, it'll get rid of any variables that are unneeded. It'll consolidate them. It'll find ones that aren't ever altered and treat them as constants, and then just throw them away. Getting back to my comment about Java, yeah, all objects in Java are just pointers to malloc memory. That is absolutely correct. When you type new in Java, you're just calling malloc behind the scenes. And variables that are objects are just pointers to the malloc memory. And when you use the dot in Java, it's the same as using the arrow in C. That's actually why some of the first C++ compilers were just C++ to C compilers. They would take all of those calls to new and replace them with malloc, and it would take all the dots and turn them into arrows, and then put stars in front of everything to dereference them. And then you just got a C program that is essentially object-oriented. So you can build objects in C out of structs. And again, in the first C++ compilers, anytime it saw the word class, it just replaced that with struct. So it's a pretty, actually easy transformation to turn C++ into C. You just take classes and turn them into structs. If your classes contain methods, then those are just function pointers. And then everywhere where you see the word new, you just replace it with malloc. You got little other transformations you have to do, but that's basically the idea. And someone, I just briefly saw a message, in first versions of C++, structs were actually just equivalent to public classes. So structs were just classes that were public by default, and classes were structs that were private by default. So that's all they were. Okay, so where does that leave us with our program here? We now have the ability to sort the Pokemons by name. It's already 11:22. Do we want to maybe show you how to do a search at this point? Or should we call it a day and say, that's enough for this week, let's go on and do that next week? What do you think?
I'm up for doing the search.
You want to do the search? Okay. I am too. We got 40 minutes left. We can do this. But do you remember last time we did, was it load file where we load file 2 where we sorted? Yeah, here we did. We did a sort. And then we were able to do, we just printed out the array. And then in the very first version of load file, not only did we load the file, we also did a search at the very end. Let me scroll through here. Did we do that search? Yeah. We said search for, we gave it a target, and then it did a linear search through the array looking for that particular word that you were looking for. Let's see, so what should I do here? Should I modify load file 2? I might as well. We've got our array of strings. We then sort the array of strings, and now we want to search for one. Okay, so let's right here, let's prompt the user, search for a target string. Prompt the user. Let's use fgetS. Let's trim off the new line if we have to. And then here's where we would have had a linear search that starts from the beginning of the array, searches through until it finds the one we're looking for, and then prints it out if we found it, and otherwise it doesn't print anything out if it doesn't find it. But since the array is now sorted, we can be more intelligent about how we search. We can use a binary search in which we start in the middle, and if that's the one we're looking for, we're done. If it's not, we can see whether our target comes before or after the middle one and essentially discard half of the remaining array every time we do that. Then we cut it in half again, discard half, cut it in half again, discard half, and this will allow us to find the element we're looking for very quickly. So there's a built-in function called bsearch that does a binary search. You have to pass it 5 parameters. And now I need to refresh my memory about what those parameters are. Okay, so it's basically the same as qsort with the addition of the thing that you're searching for. So the first parameter is the thing that you're searching for, which is our target. Second parameter, the array that we're searching through, which for us is called entries. Third parameter, the length of the array. Fourth parameter, size of each element of the array. In this case, they are all character pointers. And fifth parameter is a comparison function. But this is not the same comparison function you used for qsort. It's a different one. Let's call this I don't know what to call this. Let's call it string search. And what bsearch returns to us is a pointer to the thing that it found. So the thing that it found is going to be the entry out of the array. In this case, it's going to return to us, let's see, where's a picture? Do I have a picture that I could use? Here we go. So as far as binary search is concerned, it is searching through this array or this array. Doesn't matter which one. It's searching through this array. Our string compare function, our search compare function, is going to actually do the actual string comparisons itself. But as far as binary search is concerned, it's just searching through this array. And so it's going to return to us the thing that it found. So if this is the element of the array that contains the string that we're searching for, it's going to return a pointer to that thing. Which means it's going to return to us a character pointer. Because it's an array of character pointers, and we'll get a pointer to one of those things. It'll return null if it didn't find anything, and it'll return a non-null value if it did find something. So here's what it found. We'll say printf found. And since we got a pointer to a character pointer, we need to dereference it, and that'll tell us what the actual string is. Else, printf, oh, didn't find it. Okay, just to recap, we're going to call bsearch. We're going to pass in the target that we're searching for, the thing that we're searching for, the array we're searching through, how long the array is, how large each element of that array is, and a function that will do our comparison for us. And then it's going to return a pointer to the thing that it found. And then if that is not a null, we can go ahead and dereference it and print out what we found. Otherwise, we'll print out an error message. Okay, so let's look at string search. So the string search function is also passed in two parameters, but the first parameter is the thing that we're searching for, and the second parameter is one of the elements out of the array. So when we were sorting the array, we were passed two of the elements in the array because we had to know whether this element was, these two elements were in the correct order or needed to be switched. But when we're searching through the array, we only need a pointer to one of the elements in the array and the thing that we're searching for. And we just want to see if those two things are equal or less than or greater than, so that we know which direction to search through. Should we search to the right or should we search to the left? So we're passing two parameters. One is the target, the thing we're searching for, and we are passed in a pointer to one of the elements of the array. So let's cast them to be what they should be. So T is, what is it actually? So when we called bsearch down here, we're passing in the target. And I need to put in a target here. Target is a string, so it's actually a character pointer. And what is this element? What is it actually? It's coming in as a void pointer, but it is actually something else. Can you figure that out? Look at this picture here. Here's element, and it points to one of these things.
So it's a pointer to a character pointer?
Good. Where it's not Pokemons, this is not the Pokemon program, this is just the program that searches through strings. We'll get to the structs in a moment. Okay, so T is actually a string, character pointer, and element is actually a pointer to a character pointer. And now we're going to return string compare. TT, which is already the correct type, It's already a string. But EE is not a string. It's a pointer to a string. So we need to dereference it. And that should do it. Okay, so it just loaded in that rocku file that contains a whole bunch of passwords. And now we'll search for something out of there, like password. I know that's in there. It's around entry number 7. And it says it found it. And if I search for something that's not in there, it says, I didn't find it. Now, let's try it with a much larger file. The one with 1 million entries in it. So remember, here it sorted that thing in a fraction of a second. And now we'll search for something like password, and it says found it. And if we search for something that's not in there, it says I didn't find it. So binary search here is really fast. Now the linear search wasn't that slow either, but this is much, much faster. So let's recap. When we do a binary search, where is it? Here it is. We pass in the thing we're searching for, the array we're searching through, how long that array is, the size of each element of that array, and then a function that's going to do our comparison for us. And it's going to pass back a pointer to the thing that it found. In our comparison function, we are passed in a pointer to our target, a pointer to one of the elements of the array we're searching through, and then we have to cast them to be the correct thing. So here's an example where the casts are different. Up here, when we were doing these string compares, they were the same because they were both pointers to elements of the same array. But here, they're potentially different. So the first thing is a pointer to the thing we are searching for. In this case, it's a string. So we can cast it to a string, a character pointer. And our element is a pointer to a string. So we cast it as a character pointer, and then we have to dereference it when we're passing it into string compare. Okay. So now that we know how to use binary search, let's try it with the Pokemons, and then that'll be it for today. Okay, so we sorted the Pokemons, we printed them out, we're sorting them by name, and now we're going to do a search. So let's type in, let's have it prompt the user for a Pokemon to search for. And then we will get that input from the user. Strip off the new line. And so P now contains the Pokemon that we are searching for. So we're going to call bsearch, pass in the thing we're searching for, the array we're searching through, which is Pokemons, the length of the array, which is not 10, it's just length, and then how big each element is. Each element is a Pokemon structure. So we'll pass in size of struct Pokemon. And then finally our comparison function. Pokemon search. And then bsearch will hand back a pointer to the thing that it found. So what's that going to be? It's going to be one of these things. All right, we're searching for a Pokemon by its name, so we're going to type in something like Charmander, but it's going to hand back a pointer to one of those structures. And so this is what I just typed in. Struct Pokemon pointer found. And then if found, we'll print out the name of the Pokemon, its hit points, and its type. Okay, so found contains a pointer to a struct Pokemon. So to dereference it, I'm going to use the arrow. So found arrow, or found pointer name, found pointer hit points, and found pointer type. Else, printf, didn't find it. Okay, so we're going to pass into bsearch the thing that we're searching for, which is just a string, the array, its length, the size of each element, and the name of a function to do our comparison. It's going to hand back a pointer to the thing that it found. In this case, it's going to be a pointer to a struct Pokemon. And then we'll print out the name, hit points, and type of that thing that it found. If it did find it, otherwise it prints out a message that says it didn't.
Should that third placeholder be a %s?
Yes, thank you. Okay, let's go write this Pokemon search function. First thing you do is cast them to be the right thing. So T is our target, and in this case, it's a string. It's the name of a Pokemon. And element is a pointer to one of the elements of the array we're searching through. So it's going to be a struct Pokemon pointer. Now, some of you might be thinking, all this pointer stuff is making my head hurt. And you're probably right. You know, back when I introduced pointers, I didn't say, like, pointers are really easy, you'll get this the first time you do it. I think that my hope is that by showing you these pointers being used in a wide variety of different ways, that you'll finally kind of be able to get your head around them. And it really helps to draw these diagrams and use an arrow to represent a pointer. So every time you see an arrow here, you should think of that. That means a star is happening somewhere in there, or actually almost literally an arrow, right? You can see this diagram here when I say AA pointer to name, I've got AA and then an arrow and then pointing to the actual field, right? So it's almost like the syntax matches the diagrams you draw. Okay, so EE is a struct Pokemon pointer, and TT is a string. So I'm going to return string compare TT, which is already the correct type, and then EE, which is not the correct type, but I'm going to go EE pointer name, and that'll be the correct thing.
On line 30, I think your right-hand side needs to be T.
Yes, thank you. That's probably what all these errors are. Nope, there's something else going on. Oh, I have two declarations of P in my program. I knew when I typed that in, I was like, don't I already have a variable called P? I hope not. Let's just go ahead and call it target. Oh, goodness, that got rid of all those errors. Always fix one error and then recompile. Okay, what Pokemon should we search for? Let's search for Rapidash. Oh, I typed in a colon. Try that again. There, found it. Abdul says, awesome. I think that's pretty cool too. So let's do one more thing, and this is just sort of out of my curiosity. Let's have it so that I don't have to type in the whole Pokemon name. I could type in just a portion of it. Like I could just type in Pika, and it would find the whole Pikachu. Or I could type in just Chew, and it would find the whole thing. So not quite searching by regular expression, but we're going to search by substring. How do we do that? Okay, you're right. We're going to use the string function, right? But it's going to be a little more complicated than this because string doesn't return the correct type of thing. We want to return either a 0, a negative number, or a positive number. We want to return a 0 if we've got a match, and a negative number or a positive number if we don't have a match. So we'll start out by using the string function to do that substring search. And if that one returned that the thing we're looking for is contained within the name, then boom, we're done. We can go ahead and return 0 at that point, because that indicates we found what we're looking for. It's not an exact match, but it's close enough. So we'll go if string TT and EE pointer name, right? And the first parameter to string is the thing we're looking for, and the second parameter is the larger name that we're searching through. So if this returned, now string returns a pointer to the thing that it found, or null if it didn't find anything. So if this thing returns basically a positive value, then we'll just go ahead and return 0. We're done. We found what we're looking for. Otherwise, we'll use that string compare function. Let's see, well, is this going to work? Now I think this is not going to work. So this is only going to work if what we type in is the first few characters of the Pokemon we're looking for, not just any random substring. So actually we should not use string for this. And can you see why this is not going to work? Right? Because if I just search for chu, C-H-U, if I do find it, that'll work fine. But if I don't find it, I need to know whether to go to the left or to the right. And these are sorted by alphabetically by their names, but their names are based upon like the first letters and the second letters of their names. And I'm searching for like something that's further in. And so the binary search is not going to work if I just search for any random substring. So I'm going to have to kind of restrict this to say what Pokemon should we find, but we can enter just the first few characters because that'll work with the binary search. Okay, but what that means is that I'm going to use not string, I'm going to use string compare, but I'm going to use the one that only compares a certain number of characters. There's string compare. There is a cousin to string compare called string n compare, which will compare strings, but it will stop at the a certain number of characters in. So if I have Pikachu, which contains, what, 7 letters, but I only enter Pika, which is 4, then the regular string compare will never say these two things are equal. But string n compare will say they're equal if just the first 4 characters are equal. So that's what we want to do here. String. So now we can just go back to return string n compare. And we'll pass in the string length of TT. So we'll just search at most it will search through the entire target string, but only a portion of the string we're searching through. So let's try this. Let's search for Pika, and it found Pikachu. And we'll search for Rappy, and it found Rapidash. But if I search for Chu, it's not going to find it because it's not one of the first characters. So unfortunately, there is no easy way to do a binary search on just an arbitrary substring because it depends upon being able to look at the first characters of the string. But I think this is pretty cool, right? We can type in just a portion of a name. What if we just type in W? Which one's it going to find? So this one found Whalmer. But it's not necessarily going to be the first one that comes alphabetically. Remember, it's doing this binary search where it's bouncing through the array. So it's just going to find whichever one it happens to stumble across first. Well, so that kind of satisfied my curiosity there, was could we do a search by a substring? And we got close, but good enough, I'd say, for me. Okay, so how does this relate to what we're ultimately going to do in this assignment? Not the load dictionary one, the one we're going to do next week. Well, you know, if you're watching this and you're kind of thinking ahead, you might be able to start putting together the pieces already. Remember, we talked about pre-hashing all of those passwords. And previously, we stored them in 2 parallel arrays. But we had this problem, which is if we wanted to sort the arrays so that we could search through them quickly, we would have to somehow sort both of them identically, so that if we rearrange two of the elements in the first array, we would have to rearrange the same two elements in the second array. And the problem is that qsort doesn't know how to do that. It can only sort the elements of one array, not of two arrays. So, do you see where this is going? Chris is nodding his head. What are we going to end up doing so that we can sort the hashes and so that the passwords go with them?
Well, we'll need to sort it the same way we did the Pokemon structs.
Yeah, so we'll build a structure that contains
put the password and hash into a structure.
Got it. The password and the hash are in the same structure. And then we'll sort that array of structures by their hash values. And of course, our program won't know how many entries that array is going to contain when we start reading in this file. So we might want to use a resizable array. As we pull in these passwords, we will hash each password, put them into a structure, and then add that structure to the array, growing the array as we need it. That's one thing we didn't do today, was grow that Pokemon structure, but we could very quickly do that on Tuesday. And then we can sort that array of structures by their hash values and then do binary search on it. And what you'll find is that for the large files, the next assignment actually includes a file that contains 3 million entries out of the RockU file, which is about the maximum size that'll fit in our meager little virtual machines that have a gigabyte of memory each. Once you read that entire thing, it'll take about, if I remember, maybe between 30 seconds and a minute to read that file in and sort it. But then once that's done, it'll crack 1,000 passwords in a fraction of a second. So that's what we're leading up towards. So I think what we'll do is on Tuesday is we'll kind of recap what we did today, and also show you how to make an array of structures that grows as you read in the values. Then you'll sort that array of structures and then be able to search through it very quickly. And that'll put together all the pieces you need to be able to do this final password cracking assignment. Okay? Now somebody asks here, can we make a smart array that contains the array and its length? You know, that's basically what the C++ arrays are. And that's what the Java arrays are, is they're just arrays of values along with a length field. And that gets around the problem of having to pass the length around separately, but it requires now like having a struct that you pass around, or a class, if you will. So that's really like why a lot of these programming languages like C and Java do arrays differently than they do in C, because they wanted to fix that like one really serious shortcoming of C, in which C doesn't know the length of its arrays. And it is the source of so many bugs in C programs, where the programmer doesn't keep track of the actual length of the array, causing overruns or underruns or whatever kind of run that just creates problems. So most languages ever since C have arrays that know their own length and keep track of their length as a separate field within a struct or a class. Same thing for strings. There was a decision made early on in the development of C in which strings would be a character array, but it has this additional null character at the end, the mark at the end. And I think the reason for that, if I remember, I read an interview with one of the early developers of C. They said, why did you do it that way? Why did you put the null character at the end where, you know, everything else was handled by keeping the length in a separate variable? Why were the strings different? Which means that basically every string takes up one more character than it really needs to. And I think their answer was, well, it was it was a trade-off at the time. At the time, computers didn't have a whole lot of memory and they were relatively slow. So if you wanted to create a string that also had a length field, you would have to then kind of build a struct out of that, right? And so you'd have this string struct, which just seemed like excess work. And one of the fundamental data types in C is the string, right? It actually has syntax for handling strings, like it has the double quote marks. And so they decided to put that null character at the end. Even though it would use one extra character, putting a length field in there would use at least 1 byte for a string up to 256 characters, or would use 2 bytes for strings up to 64 kilobytes. And so I think they made the decision that they would use 1 extra byte for a null rather than 2 extra bytes for a length field. But the downside is now you got to move these null characters around. All of your string handling functions depend upon that null character being there, and if it's not there, they break. It would have been better, the interviewee said, it would have been better in hindsight to have passed around a length field, and then that way the string functions would just go up to whatever that number was and then stop. But it was a trade-off made at the time where they decided the 1 byte penalty was better than a 2 byte penalty that you would always have to pay, or a 4 byte penalty if you wanted to make strings that were longer than that. Oh, and then Nuno says the length then will also have to be updated every time you modified the string, which was a bit of overhead as well. You might as well just move that null character around. So, you know, everything in language design is a trade-off. Anything almost anywhere is a trade-off between competing sets of criteria, and you trying to find like that middle ground in between what you want to do and what you can do. Anyway, it's 12 o'clock now. I think we've reached the end of today. Why don't we end it here? So start thinking about, and you can go ahead and you can look at the next assignment if you want, and you should probably at this point have pretty much all the pieces to be able to do that. The one thing you probably don't have is how to extend that array of structures, but hopefully you can figure it out. I've given you enough information that you could probably figure it out on your own how to do that. Okay. So yeah, we did learn a lot today. We learned how to make arrays that extend themselves. We learned how to sort an array of structures, how to search through an array of strings and search through an array of structures. Yeah, it was a lot of stuff. But we did it. So, whew, got all that done. Now, try to figure out how you can apply that, not just to, you know, these particular assignments, but, you know, could you write a program this weekend that just uses those concepts in something else? You know, maybe a program that holds information about, you know, friends, you know, name, email address, age, you know, whatever else, and then some way to search. Maybe you could have a little menu that says, do you want to search for someone by name, or do you want to search for them by email address? So think about doing something related to that. Anyway, it's past 12 o'clock. I'm glad you all could make it, and I hope you all have a great weekend.
All right.
Yeah,
Thank you.
Chris? All right.
All right.
Yep.
Bye.
Take care. Bye-bye. And I saw a comment on YouTube that says, is this an actual college class? And yes, it is. So that voice that you hear, that's not me, is one of the students in the class. And I'm simultaneously streaming this to Zoom, where they are. They can see me and I can see them. And then also on YouTube, where I can only just see you. as far as names they're going by on chat. But I am making this content available for anyone on YouTube to come and watch and learn a little bit about C programming. And so I hope you enjoy it. And so this is every Monday, not every Monday, every Tuesday and Thursday at 9:30 in the morning Pacific time. That's United States Pacific time. And then on Mondays and Wednesdays, I have a different course, also a college course called Discrete Structures. It's kind of like discrete math, but for computer science. And we are currently talking about finite state machines. So you can check that out on Mondays and Wednesdays at 9:30. So same time, just different days. So Tuesdays and Thursdays for this particular course, Mondays and Wednesdays for the other course. We got about 4 weeks left in the semester. Also, all of the videos for this semester are on YouTube, so you can go through my channel and just scroll backwards through. You can find my playlists for C programming and discrete structures. You just scroll backwards and go all the way back to, I think we started in late January, so that's when the first lectures would have been, and then go forward from there. Yep, Nanya just confirmed what I just said. You can watch all these series from the very beginning if you want. Okay, so I hope you all have a good weekend, and I will see you on, well, Monday if you want to see the other course, and Tuesday if you're sticking around for the C course. Have a good day. Take care. Be safe. Bye-bye.